Hello everyone, today I'm going to explain the metabolic differences between normal cells and cancer cells with a special focus on Warburg effect. We will look at why cancer cells consume glucose in a completely different way from normal cells and how this metabolic shift supports cancer growth and immune invasion. First, why do we compare the metabolism of normal cells and cancer cells? Even though cancer cells carry the same genetic information as normal cells, their energy strategies are dramatically different. Changes in glucose usage and oxygen dependency are crucial clues for cancer diagnosis and therapy. So, the key question we need to ask is, why do cancer cells choose a less efficient metabolic pathway? Normal cells prioritize energy efficiency. Glucose is converted into pyruvate through glycolysis, and this pyruvate enters the TCA cycle and electron transport chain in mitochondria, producing about 30 and 32 ATP per glucose molecule. They switch to lactate fermentation only when the oxygen is limited. So, under the normal conditions, mitochondrial oxidase phosphorylation is always preferred. But cancer cells make a very unusual choice. Even in the presence of sufficient oxygen, they excessively activate glycolysis and continuously produce lactate. This phenomenon is called the Warburg effect. Cancer cells take in 10 to 50 times more glucose than normal cells, which is why cancer tissues appear bright on PET-CT scans. The Warburg effect is one of the most defining features of cancer metabolism. When we directly compare the metabolic strategies of both cells, the difference becomes very clear. Normal cells rely on oxidative phosphorylation, producing energy efficiency. In contrast, cancer cells rely heavily on glycolysis and lactate fermentation. They overexpress GLUT1 to maximize glucose uptake and increase LDHA to maintain lactate production. And instead of using TCA cycle mainly for ATP production, cancer cells diverted toward biosynthesis to support rapid cell division. So, why do cancer cells intentionally choose a less efficient metabolic pathway? Here are the five major strategic advantages. First, ATP speed matters more than ATP efficiency. Mitochondrial ATP production is efficient but slow. Glycolysis, however, generates ATP extremely quickly, which supports the rapid cell division rate of cancer cells. Second, glycolysis supplies large amount of biosynthetic precursors. 3-PG becomes serine and glycine. Citrate becomes fatty acid, and the PPP produces ribose and NADPH. These materials are essential for building DNA, membranes, and proteins. Third, the mitochondria in cancer cells are not broken. Cancer cells use a hybrid system, both osmose and glycolysis, switching between pathways to maximize survival and growth. Fourth, the tumor microenvironment is hypoxic. Under low oxygen, HIF1 alpha becomes stabilized and increases GLUT1, LDHA, and PTK1 expression, forcing cells to rely even more on glycolysis and preventing pyruvate from entering the mitochondria. Fifth, lactate functions as an immune suppressive signal. Accumulated lactate lowers the pH, which weakens T cells, NK cells, and dendritic cells. So, lactate activity helps cancer cells evade immune attacks. Therefore, the Warburg effect is not metabolic inefficiency. It is a strategic reprogramming that supports growth, immune invasion, and hypoxia adoption. The Warburg effect is maintained through several coordinated molecule changes. Overexpression of GLUT1 dramatically increases glucose uptake. Increases HH2, PFK1, and LDHA, raises overall glucose flux. Increased PTK1 inhibits PDA so pyruvate cannot enter the mitochondria. Increased MCT4 rapidly exports lactate to acidify the environment. These mechanisms work together to keep glycolysis running at high speed. This metabolic strategy offers clear advantages for cancer cells: faster ATP production, abundant biosynthetic precursors, strong adaptation to hypoxia via HIF-1 alpha, immune invasion through lactate accumulation, formation of an acidic microenvironment that inhibits normal cells. Overall, the Warburg effect allows cancer cells to secure both rapid growth and survival. These metabolic characteristics translate directly into therapeutic targets. GLUT1 inhibition blocks glucose supply. LDHA inhibition blocks lactate production and stops glycolysis. PDK1 inhibition forces pyruvate into the TCA cycle, then increasing stress. MCT4 inhibition prevents lactate export, causing cancer cells to acidify themselves. And GLS inhibition blocks glutamine addiction. Thus, targeting cancer metabolism is a central strategy in modern anti-cancer drug development. In conclusion, the Warburg effect is far more than just producing lactate despite oxygen. It is a metabolic reprogramming that enables cancer cells to grow rapidly, evade the immune system, and survive in harsh environments. Cancer cells choose speed, biosynthesis, and immune escape, while normal cells choose efficiency. Understanding these metabolic differences is essential for grasping the true nature of cancer and for developing next generation anti-cancer therapies. Thank you for listening.